Okay, so we're on record. Let's start with any questions. No questions? Okay, so let me start with two general remarks. So first of all, about the mode of lecturing, you probably already noticed. So I'm not trying to compete with textbooks. I'm not trying to write a textbook. So there are many textbooks on the subject. I gave one of them on the course site, but yes, there are many others, and you can also look for information on the web. As I say, lots of information on the web. So it means that sometimes I will not give all the details. I basically will assume that you also will read about the subject either before the lectures or afterwards. I personally think it's better practice to do it before, but it's a matter of taste. And what I will try to do is to give some added value to say those things that are not written well in textbooks, or at least I think I can say something else. So of course I will try to be consistent and will not miss parts, but I I will probably miss lots of details uh, because I really think I don't have a contribution there. Um, yes, so for this reason, probably the most important part is your questions. So if you try to understand something and did not understand it from the web, from textbooks, from these lectures, and then the best thing I can do is to help you to understand it. So if you try to come up with questions, if you try to understand something and don't understand it well, and if you have any questions, so feel free to ask all the time. Mm. So the second thing is about email list. So Guy Capone is here. Guy, are you here? So it seems that Guy is not here. Okay, so I talked with him about email list. So the best practice is to register via the FGF site. Um, Even if you're not vice president student, I think it's possible. If you don't sure how, just write email to the administrators there. But in any case, you can ask to add you to the email list. Just send Guy an email. Everybody know how to find Guy's email? If somebody don't know, so you can ask. So send him an email, ask him to add you to the email list, and I will ask him each time that there is some announcement, both to do it via the FGS site and via the email list if somebody have problems with the FGS site. Um, okay, so let's talk a bit more about examples of categories in some more detail. So it's somehow digression from the main part of the course. So we discuss the notion of overcategory. If we have some object X, we have the overcategory of X. And if X is a topological space, then there are many different overcategories which are interesting. And I wanted to discuss some examples. So the first examples that we already discussed are fiber bundles. Okay, maybe another general remark. As you probably notice, my spelling is disaster. I have dyslexia. So I will write in abbreviations, but anyhow, there will be lots of mistakes. This is what we have. But if something not clear, then ask me and correct me, of course. So fiber bundles are maps from say y to x, which locally on the base are isomorphic in the over category to products. Yeah, phi of u. So it means that we have an open cover of x from open sets, such as for each open set, when we consider this object in the over category, this object is isomorphic to the object. So what happens here? U times f to u. Great. Okay, another important special case are covering spaces.
Can you explain again the fiber product
There's
example?
no fiber product here. There is already notion of there's only the notion of fiber bundle. Should I
Fiber
explain again the
bundle.
notion of fiber bundle?
Yes, in the over category. How
So
can say?
we have the we have the over category of X, and now Y. It considers a subset of all objects, a subclass of all objects. Y to X are objects in the over category of X, such that there exists open cover X equal to union of UI, open cover, such that phi inverse of UI, phi restricted to phi inverse of UI is isomorphic. Isomorphic in the over category to UI times F. Let's call it Fi. It a priori can depend on UI. A posteriori, if X is connected, then it cannot depend on it. MUI projection. Okay, is it more clear than before?
This is a definition using the over category, right? This is idea.
This is a definition of the notion of fiber bundle using the notion of the over category of X. So, and the category of fiber bundles is a full subcategory of the over category. So I don't need to define what are maps there. I just specify a set of objects, and this is it.
So, but okay. So, but the over category. So the map should be part of the over category, right?
Yes, yes.
But
So object in the over category is such a triple or pair, depends how you count.
oh, on itself. Okay, on it. Okay.
And morphism is in the over category. We discuss its maps such that the diagram is commutative. Okay. So we have fiber bundles. Now we have covering spaces. Covering spaces are basically the same as over category, as fiber bundles, but the fibers, the Fi, have to be discrete. So covering spaces, the same, but Fi have to be discrete. Okay. So now another notion of, in fact, notion of a sheaf. But the notion of a sheaf have several definitions. A posteriori they are all equivalent, but for now we will consider them as different. So I will call it Leray sheaf. So in the literature, you will usually not find the word Leray because they're just different definitions, and this is definition of Leray, which is historically the original definition of sheaf. So what is a Leray sheaf? So it's again, the category of Leray sheaves is again full subcategory in the over category. So we take all y vx. And this time the condition is like this, that locally on the source, the map is just homeomorphism. So let's write it. Exist y שווה union ui open cover such that phi restricted to UI when considered as a map from UI to its image, phi of UI, is homeomorphism, meaning isomorphism in the category of topological spaces. So as you can see, exercise coverings of its full subcategory of Schlerer sheaves. Which is nice. So we will discuss more definitions of more equivalent definitions of sheaves later in the course, and we will talk about what it means that they are equivalent.
Is a sheaf a particular case of a fiber bundle?
Mm, no, or at least not in this point of view. No, in general, no, because it's the condition is only on the source. So open embedding also gives a sheaf, but open embedding is not a fiber bundle. Okay. So for there are other notions which I will not discuss now in details, but I just will tell you that they exist. So the notion of local system. So local system is basically the same like covering space, but covering space is local systems of sets. But we can discuss local systems of abelian groups or vector spaces or anything else. And it basically means covering spaces where the fibers have this additional structure of abelian group, of vector space, of algebra, of whatever you want. So these local systems of something. And you have the notions of sheaves of something, of abelian groups, vector spaces, etc. Again, those are sheaves, such as the fibers have this additional structure. And of course, this additional structure have to be continuous. So I will try to discuss it in general in several lectures, but now we just give you the hint. And similarly, you have the notion of vector bundle over, and here you have to choose some field, and it's the field have to have topology, otherwise it doesn't really make sense. So let's start with R. You can do it for other fields too, but you can't do it just for general field. You need topology. And here the idea is again the same. It's like fiber bundle, but the fibers have a structure of a vector space, and it has to be continuous. So I will not specify exactly what does it means, but you can, first of all, you can read it on the web. It's not crucial for the course. And secondly, I will say in general how to specify what does it mean without, not in each case separately, but in some general system. But this will happen in several lectures. Okay, so those are some important examples of subcategories of the overcategory in case of topological spaces. And you have similar things when you discuss smooth manifolds. Then you have to also incorporate the smooth structure, and you see in other geometric settings too. Any questions about that? No questions?
If you can explain more about shifts, if it's the topic right now.
Um, uh, at this point, I just wanted to give the definition.
Or of local system.
Local system. So local system is a covering space, such as on the fibers you have additional structure. Depends local systems of what. Local system of sets is just a covering space. Local system of abelian groups means that in each fiber you have a structure of abelian group. So local systems. Okay, covering spaces are often used in topology in different contexts. When you talk about local systems, it means that you basically want to talk in the context of sheaves. So it's covering spaces, but you consider them as a special case of sheaves. And this is one of the ways to think about covering spaces, or one of the ways to think about sheaves, like generalization of covering spaces. So covering spaces are sheaves which in all points look basically the same, because locally they look like projection with a discrete fiber. And other sheaves, so for example, if you have open embedding, this is also a sheaf, but it's not a covering space, so it's behave badly when you go to the edge of your open space, to the boundary of your open space. And also maybe one thing that I should say is that in many popular, so this definition of sheaves is a bit misleading, because in many important examples of sheaves, they can be treated via this definition, but the space Y is not Hausdorff, and it's kind of a disaster. Yeah, so you start with some very nice sheaf with respect to some other definitions that you want to discuss, and the space Y look like total disaster, very not Hausdorff, and how to comprehend. So this why is our other approaches to sheaves too. Okay. So now I wanted to talk about diagrams. So what is a diagram? Let's try to be formal. So we start with a graph gamma, usually finite graph, but it doesn't have to be. And now you have definition. Oops, what happens here? Okay. Definition. What does it mean? A diagram of shape gamma. So let gamma be a graph. A diagram in a category C of shape gamma. Now I'm not sure I will write it. So it's an assignment for each vertex of gamma an object, and for each gamma is directed graph, yes. And for each error in gamma, a map between the two objects. So let me write something. Is an assignment var of gamma to objects in C, and edges of gamma to morphism in C, such that something happens, such that yes, so you can guess what is the condition that the errors are between the correct vertices. Yes, so maybe I should say something about this notation. If you have category, sometimes it's nice to talk about the set of all morphisms in this category, no matter what is the beginning and what is the end. You just put them all in one big pile. And this is a collection of morphisms of the category. Okay, so is the definition of diagram is more or less clear? Oh, is it clear? It should be easy. So is it clear? Okay.
Can I ask a question about the definition of diagram?
Yeah, of course, of course.
Yeah, that so you have two vertices, they go to two objects, and the edge between them, it doesn't matter will it go from A to B or from B to A. So the graph.
No, the graph is directed graph.
Directed. I see.
And
Sorry.
the edge should go to the correct direction.
Thank you. Thank you.
And now we want the notion of commutative diagram. Commutative diagram is a diagram such that, so if we have okay, if we have two facets between two vertices, then the corresponding compositions coincide. Yes, so we have two vertices and two passes. So to each vertex we have to each arrow to each edge we have a morphism. So we can take one composition, can take the other composition. We want them to be the same. Okay, this is a notion of commutative diagram. Okay, so the collection of all diagrams of the same shape form a category, and also the collection of all commutative diagrams of the same shape forms a
Professor, we don't hear you.
Okay, sorry. So when did you stop to hear me?
In point 3.
From the beginning? Okay. Okay, so a morphism between two commutative diagrams of the same shape, of shape gamma, is a commutative diagram of the of corresponding shape that's like constructed from those two diagrams. Of two commutative diagrams, let's call it D1 and D2. In the commutative diagram, okay, I will just say it in words. So we have D1, D2, not in words, but in example. So we have here some shape. So here we have exactly the same shape. And now we have to add arrows, each vertex to the corresponding one. And we want this union with those arrows to be commutative diagram. Is it clear?
The set of objects, the set of vertices are the same, right? Always.
Of the two diagrams, they have to be
Yes,
just of the
precisely.
same shape, the same vertices, the same morphisms. And then you have, then you construct a new commutative diagram which have twice more vertices and twice more, and morphisms, all the old morphisms, so twice more morphism plus additional morphism for each vertex of the original diagram, like in this case +4. Okay, I can spell it all out, but I think it will be too long. So, is it clear what is the morphism between two commutative diagrams?
Yes.
Okay. And then there is a notion of morphism between two general diagrams. Here you cannot cheat. You cannot say that what you get is a commutative diagram, but the way basically what you want that each time you have morphism in one diagram and morphism in the other diagram, then this small diagram, 2x2 diagram, will be commutative. Yeah, so 4 may be an exercise. Define, it's not well defined exercise, but I think it's okay. Define notion of morphism of diagrams. Okay. Okay, so now there are some interesting special cases. For example, category of arrows category of arrows is just category of diagrams. So maybe I should put this notation, just a moment. Yes, so a diagram, commutative, okay. So let's put it here, notation. Diag gamma of C. And also we have commutative diag gamma of C. Yes, so we have notation for the category of all diagrams in C of a given shape gamma, and category of commutative diagram of a given shape gamma. So category of diagrams of this shape, like the simplest possible shape more or less, is called the category of arrows, or category of morphisms also.
What are the objects and what are the morphisms?
So the morphisms are diagrams of this shape, meaning pair of two objects and morphism between them. And morphisms are morphisms of such diagram, meaning diagrams of this shape, a commutative diagram of this shape. And as you can see, both the over category and the under category are both full subcategories of the category of diagrams. Yeah, and what we often will do, we will consider categories like the over category and the under category. The over category is not a special case of the category of category of diagrams. It's not category of diagrams of any particular shape. It is a full subcategory of this category. And this is often something that we will do. We will consider the category of all the diagrams of all commutative diagrams of a given shape, and then we will fix sub diagrams there, and then we will, or subset of objects or sub diagram, and we will require that all the objects will look exactly like this. Or in all diagrams, this will be, we will fix sub diagram. So yes, this is something that we will often do. We will not have a special notation for that, but it will be relevant. Okay, I think enough with examples, and we can go to our first categorical construction, the construction of initial objects. Are there any questions before that? No questions? Okay, so in category theory we have many constructions, and basically all the constructions looks the same way. We define some notion, some objects that satisfy, or something that satisfy A, B, C, D. Then we will prove that if such objects exist, then it's unique, or unique up to a unique isomorphism, in fact, usually. And often it will not exist. So when you define some categorical construction category theory, you define it in generality of a general category, and usually often it will not exist. But for some interesting categories, it will exist. There are sometimes some general theorem that says that under some conditions it exists, and even if not, then in some interesting special cases, you show that it exists. And the part where it's make your life easier is that you don't really need to prove that it's unique, because it's something that you prove once and for all. And the advantage is that, like, if you look at the proof that something like this exists, it's often give a construction, so you can use it as a definition. But there are many different constructions and many different definitions, and you want to know that they're all the same. And if you have some notion, you can formalize it as a categorical notion, it means that now you only care about the construction and you don't really care about defining what it is exactly. So another remark that there are several approaches to how to define all categorical notions. In a sense, they're all special case of more or less any one of them. So one out of three of them. So I will now define an initial object, and in a sense, all the other categorical notions will be a special case of this construction of the initial object. But of course, there is some translations there, and sometimes this translation is complicated. And also there are some other important special cases which are also, in a sense, general special cases. So everything is a special case of them, just with different translation. So we'll start with initial object. So definition, initial object in a category C is an object such that an object such that an object X such that for any Y in C. So when I write Y in C, I mean Y is an object of C. More from X to Y consists of one element. So an object such as any, for any other object, you have a unique morphism from the initial object to this other object. So let's do examples. Let's start sets. Who wants to give me an initial object in sets?
Empty set.
Somebody told the answer, but then just switch off the microphone at the middle of the answer. So can you do it again?
Empty set.
Empty set. Yes, from the empty set, you always have a map to any other set. Yes, so sometimes in set theory, it's a bit confusing. What does it even mean? A map from empty set to another set? Why it's maybe it is also there is no such set. Maybe it is an empty set. But yes, if you work in set theory accurately enough, then you see that it's basically the only possible definition of what maps from empty set is. There's just one unique map from empty set to any other set. And here you also see something funny, which you don't expect usually, is that the empty set is actually the only initial object. So we'll prove in a moment that the initial object is unique up to a unique isomorphism, but it's not absolutely unique just as an object. And for the category of sets, it is, which is kind of surprising. There's only one empty set, which is also kind of sometimes a counterintuitive fact. I remember, I think in 5th grade, when they told me it, I was kind of surprised because there is the empty sets of all numbers satisfying x equal x plus 1, but also there is empty set of all cucumbers which are of mass larger than the Earth. And I was sure that there are two different empty sets until I understood that they are the same, or somebody told me that they are the same. So other examples, topological spaces. Somebody? Okay, it is just the same answer, empty set. So, and let's assume that nobody answered because it's too easy. So let's do something harder. Abelian groups.
Thought by the definition of topological sets, we exclude them, but I don't know. According
What?
to no,
Empty space, okay. It's a topological space, it's a good one. Okay, let's do abelian groups.
0.
0, the trivial abelian group. Or general groups, the same answer, the trivial group. Because you have a morphism from the trivial group to any other group, just a unique one. Pointed topological spaces. So pointed space is a space together with a point inside it, and the map between two pointed spaces is maps the designated point to the designated point. So what is the initial pointed topological space?
a point.
A point. So by the way, in the last two examples, you already see that the answer is not unique. Yes, there are many different points. They're all isomorphic as pointed topological spaces, but they're still different. and many different trivial abelian groups or trivial groups, because you can call this element in what names that you want. Okay, so in the last 2 minutes of this hour, I just want to say the proof of the fact that the initial object is unique up to unique isomorphism. So theorem, initial object is unique up to a unique isomorphism. Yeah, it's a very easy proof, but I think it's worth just to think about it for a moment. You have, you know what, maybe we'll do a break. You will think about it during the break, and then I will say it after the break, so you will have some time to do it yourself. So I'm leaving everything open except the camera and the microphone, and we will meet in 10 minutes.
Yes, we can.
Okay, I do recognize somebody that was asking questions before and now he's not here. I just don't remember his name. No, so maybe we'll wait for another minute. So yeah, I said 10 minutes and it was for. Do you have any questions? Oh, I think I see him here now. Yes, you just didn't open the camera. Yes, your thumb. So now I see everybody. Okay, so I see that guy is not here. And so I want to suggest maybe one of you will volunteer when I say some exercises. You can write them down and at the end send them to Guy, so he will be able either to incorporate them into the homework or to discuss them in his session.
I can do it from now.
Great. Okay, so you want to volunteer for the entire course or only for this lecture?
I think if I want to be in some lecture, I will ask someone else.
Okay, great. So, so, okay. So now I want to tell the proof of the theorem. Why, if there is an initial object, it's unique. It doesn't have to exist, but why it's unique. So suppose we have two initial objects, x and y. So, since x is an initial object, there is a unique morphism from x to y. Since y is an initial object, there is a unique morphism from y to x. So we have two great candidates for the isomorphism. So now we have to prove that they're actually inverse one of the other. So let's do the composition from x to y and from y to x. We will get some morphism from x to x. Anybody have an idea how to prove that this sum object is, morphism is identity?
Because there is a unique morphism from X to X. And
Yes, x is an
there is
initial
the
object,
identity
so there
from
is unique morphism from x to x. And again, the composition is some morphism from y to y, but some morphism meaning the only one morphism which is identity. So very simple proof, but if you didn't saw it before, so I think it's quite instructive. Okay, so now we can, based on this notion of initial object, we can define lots of other categorical notions. So the first one is a terminal object. So the lazy definition of the terminal object is an initial object in the opposite category. But of course, you can say, what does it mean? It means that there is a unique morphism to the terminal object. So let's do examples. Sets, who is a terminal object?
A singleton.
Exactly. Singleton, any set have a unique morphism to a singleton, because you just have no choice. And here you already see that the terminal object is not unique on the nose. There are many different singletons, but they're all canonically or uniquely isomorphic. There is a unique isomorphism or bijection between any two singletons. Topological spaces, again, singleton. Abelian groups or just groups? Anybody?
0.
0, the same as the initial one. So here we have to be a bit careful. What do we mean by the same? In category theory in general, we don't compare two objects saying that they are equal, and indeed they doesn't have to be equal because there are many different initial and many different terminal objects, but they're all isomorphic, and more than that, they're uniquely isomorphic because if we have the initial object and the terminal object, because the initial object is initial, there is a unique morphism from the initial to the terminal. And because the terminal is terminal, there is a unique morphism from initial to the terminal. So there are two good reasons why the space of morphism between them is singleton, so there is only one morphism. And we see that sometimes this morphism is an isomorphism and sometimes not. In sets it's not. In pointed set it is. In vector spaces it is. In abelian groups it is.
Rami, you can even say more explicitly that by this argument, each initial object is if you have an isomorphism between initial object to terminal object.
Terminal object, then it is
then they
the
are
only
the
one.
same. No,
Then,
even all the copies are both initial.
yes, the
and
collection
terminal.
of initial objects is coincide with the collection of terminal ones. Yes, you're right. But this is exactly something that we usually try not to do in category theory. In this case, it works. It's actually the same collection, but we want to think of the initial object as one, although it's not well defined, but it's defined up to unique isomorphism. And when we compare initial object and terminal object, we say that they are canonically isomorphic, or in this case, there are unique isomorphism between them. Yeah, so you will hear a lot, both in category theory in general, in mathematics, the notion of canonically isomorphic, when two objects are canonically isomorphic. And if you want to define this notion on the widest range of usage, then it's not a mathematical notion. It's not well-defined mathematical notion. So my teacher, my supervisor, was always saying that an object is canonical if any two experts on the subject will agree that it is canonical. And indeed, there is some gray area, what is canonical and what is not, but usually it's rather clear. But the best way for something to be canonical is to be unique. And in general, canonical it's unique when you ask it to satisfy some additional properties. It usually works. But indeed, there is some shady area of what is canonical, what is not.
Rami, is there any, when you ever say like you think of them as the same object or such, is there any notion of we can make up that there will be the same object, some equivalent class or something?
Of course, you can take isomorphism classes and then there will be isomorphic, but it's not enough. Yes, so there are very different objects which we want to think about them as different, and they are isomorphic. So what I said a minute ago, yes, that there is this idea of canonic isomorphism, and if two things are canonically isomorphic, then we will think about them as the same. But it's not an actual equivalence relation. It depends on the context. So if you have two objects, the best thing that you can ask is whether they're isomorphic or not. If they're isomorphic in a sense, you can think about them as the same. If it's just two objects, then maybe it actually makes sense. And if not, then certainly not. There is no some class of isomorphism which is better than the other, which we will call canonical. Yes, it's not work like that. If you have some additional context, then you can say that some morphism is some isomorphism is canonical as opposed to others. But for two specific objects, if there is no additional context, then there is nothing more to say. Maybe except for one exception, if the morphism is unique, if the isomorphism is unique, then it is canonical from any reasonable point of view, because so canonical means that there is one way to choose it which is better than all the others. And what is better than all the others, it depends on your point of view and depends on the context. But if it's unique, then it doesn't depend because there are no others. Where is my water? Here it is. Okay. So you see that the initial and the terminal object might be the same or isomorphic and might be not. Let's see whether we have other interesting examples. I think that not. So we can go to product and coproduct. So what is, let's start with product. We have X, we have Y, we have Z. So we have diagram of this shape. We have like two objects in the over category or two objects mapped to some other object. And we want to define product of, no, sorry, I wanted to start with product, not fiber product. So sorry, I have X and Y. I want to define product. So I consider the following category. So okay, definition. Let X and Y be in C, some category. So just ad hoc notation, CXY is kind of the over category of both X and Y together. So let me define it. It's category of all diagrams of this shape. Yeah, maybe. ZC. Yeah, so we said before that we will often consider diagrams, the category of all diagrams of a given shape with some given subset of vertices when we know what objects to put there, and we let all the other run. So here we fix X and Y, and then we consider all diagrams of this shape. Okay, so X times Y is defined to be the terminal object in CXY. So what does it mean? It means that so here there is some very common abuse of notation.
What are the
So
morphisms?
in CXY,
Yes.
so those are the morphisms of diagrams. Okay, I will. It will be implied when I will just spell out this definition. But just one thing I want to say. There is a very common abuse of notations here that you see all over mathematics. When I say X times Y, under this definition, it should be object here in this category. So it should be a triple, an object in C and two morphisms. But by abuse of notation, it's usually when we say X times Y, we mean this one, the object in C. But it always implies that it's equipped with a structure that it has two morphisms, one to X and one to Y. Like you usually do, say, in vector spaces. Vector space is a set of vectors, an operation of addition, an operation of multiplication by scalar, an element zero, such as some axioms works. So it's in fact should be a tuple and not just one set. But you often say let V be a vector space, and then let V little in V capital. And of course you don't, when you say V is vector space and V little in V capital, you don't mean that V is one of these tuples, so either the vector space itself or the operation or something else. You mean that it's vector in the vector space. So this is very common abuse of notation, and we'll do it here again and again. So the fiber product is a triple of this type. What?
Please explain what are the objects and morphisms in CXY?
Okay, so CXY, maybe I should write it like this. It's inside the AG. No, it will not be full subcategory. Okay, so objects of CXY explained here. So now let me use this trick. morphisms more between z, x, y and z prime x, y all the phi in more z, z prime, here alpha, beta, prime, beta prime, such that z, z prime, x, y is commutative.
So it's not like exactly like the morphism of diagrams.
It's
because
not a full subcategory of the category of diagrams. Yeah, it's the same like we had in the over category. So the over category, it's a subcategory of the category of diagrams. It's not a full subcategory, because we also wanted the maps on the fixed objects to be identity. And we will always have this. So in fact, you can define notion diagrams, say gamma inside gamma prime. So if you have two graphs, one in the other, so you can talk about diagrams when you fix. No, but it doesn't work like this. Sorry. Yeah, so it doesn't work because you need more data. You need also to have some given diagram here. I don't know. D. Yeah, if you have two diagrams, gamma and gamma prime, and gamma is subdiagram of gamma prime, and you have a diagram D of shape gamma, then you can define a category of all diagrams of shape gamma prime, where the subdiagram of shape gamma is just equal to D, and it's fixed, and all the morphisms there have to be identity. So you can do it, but okay, we need it for several special cases, and each time it's probably cheaper to say each time what do we mean. Okay. So is this oops, what no, I wanted to move this to this is it. So I will erase it. I erased the wrong thing. No, I didn't want to move it. Never mind, I already moved it. So is the definition of just a moment, of CXY clear now? Anybody?
Yes.
Okay. So x times y is a terminal object in C x y. So let me spell out what does it mean. We have x, we have y, we have x times y. So again, you have this abuse of notation. So x times y is both all this diagram and only this guy. And what do we want? We want it to be terminal object. So it means that for any z and for any two arrows like this, there exists and unique an arrow like this, such as the diagram is commutative. Okay. So let's do examples of product sets.
isn't it the other way around?
It is the other way around. Sorry. Yeah, it's terminal object and not initial one. So sets, what is a product? Anybody? Did you hear the question? Do you hear me?
Yes, we hear you.
Okay.
So you know what is a product in sets?
Maybe Cartesian product.
Yes,
the
yes, yes,
usual.
yes. So in general, many of notions in category theory comes from sets. So usually the name coming from there. So x times y, the Cartesian product of two sets equipped with these two projections, projection to x, projection to y. And now you see what if you have another object, z, with maps to x and y. So by definition, it means that you can map it to x times y. Just first coordinate go to x and second coordinate go to y. Okay, use the first map in order to write the first coordinate, and the second in order to write the second one. Okay, groups. Somebody? Groups.
Direct product.
Direct product of two groups. They, as a result, they have to commute, but just see the same construction work. You have two projections and you have a unique map like this. And basically all the reasonable examples will give you the reasonable notion of a direct product. So it might become a little bit more tricky when you do products of more than two objects. So everything that I said now also works for more than two objects. So of course, if you have finitely many objects, just the same, you can do it as iterated product, no problem. But if you do it for infinitely many products, then it's become interesting. So for example, in topological spaces, you get the notion of a product of topological spaces. And maybe first time you see this notion is a bit confusing. Because when you define product of topological spaces, you say that point-wise is just product, but open sets are not really what you used to. It's just weak topology. Yes, in finitely many cases you can do whatever you want, but then you have to choose the entire space. And you can ask why. So here is one good reason why, because this what corresponds to the categorical notion of a product. And the same you have with vector spaces. So exercise product of vi. So you probably know that in vector spaces, if you have infinitely many vector spaces, you have two different notions. You have notion of direct sum, which means a choice of a vector in each of the vector spaces, such that almost always it will be zero. Almost always meaning all but finitely many. And you have direct product, which means that you can take everything. So do you have a guess what would the product correspond to? It's not hard to guess. It has to be the product because this is the motivation for the name. All the series, yes. Or it's even not a series, like functions if it's not countable, yes. So exercise to verify it. Yeah, so a priori it's not clear why to choose one or not the other. So for product is this. The other will be in a moment. Okay, another exercise in general category, A times B times C equal to A times B times C and equal to A times B times C. So I define this triple product, just repeat the definition for product of two objects, but with three objects. And a priori it might be different for all those, but I claim that they are the same. And again, what do I mean by that they are the same? Okay, so first of all, it's a bit confusing because we can consider them as all objects in C, in our original category, let's call it calligraphic C. So A, B, B, C are objects in C. And in this sense, what do I mean? That they're all isomorphic. Sorry, if I consider all those objects as objects in C, that they're all isomorphic. But in fact, you can be a bit more accurate. Each of those guys is also object in some, is in its own category. Yeah, so this is object in the over category, or this C, X, Y, when X and Y are those two guys. And this is, so each of them is object in some different category. And okay, maybe I will, I will put it aside. So for now in the exercise, all what I ask is just to prove that the three of those are isomorphic. And this isomorphism is not unique. Okay, maybe I will say it in a moment, but it's not unique. It will be unique if you will put some additional conditions on this isomorphism. So you can try to put these additional conditions and then see it's unique. Or maybe another exercise, rather stupid one, but maybe important. We say that x times y, so suppose that c x y and c prime x y are products. So we say that there are more than one product. So the product is unique up to unique isomorphism, but in the corresponding category. But now, oops, sorry. If we consider C and C prime just as objects in C, yeah, so X and Y are in C, is it true that C isomorphic to C prime? Is this isomorphism unique? So I will tell you the answer for this question. The answer to the first question is yes, they are isomorphic, and the isomorphism is not unique. It's unique if you require something more, but it is not unique. Or in general, of course, you can find some degenerate examples where it would be unique, but usually not, and it's very easy to find such example, but first time it's worth to do. To convince yourself that it is important to ask whether it's unique or not. And this is exactly the case when we say that two things are canonically isomorphic, although there is more than one isomorphism between them, but somehow there is one isomorphism which is better than the others. Because if we just, and it depends on the context, because if we just look at this object with C and C prime, somebody will give us out of the blue those two objects, then of course there will be no any designated morphism between them. There will be isomorphic, but this is it. But if we're not given them out of the blue, we are given them as a product, so we're given them together with those diagrams, then of course it will be much more reasonable to consider isomorphism between them that respects those diagrams. And then such isomorphism will be unique, and then we can say that this is canonical isomorphism. And those two objects are canonically isomorphic. So whether or not two objects are canonically isomorphic depends on the context, how you got those objects. Okay, so this was about product. So now let's do coproduct. Definition, coproduct. So again, the lazy definition, coproduct is a product in the opposite category. But of course you can spell it out. So coproduct, we have X, we have Y, we have X coproduct Y. We have two maps like this, and this should be initial object in the category. Each time we have such maps. we have a unique map, a unique horizontal map. So example, coproduct of sets. Any ideas?
Disjoint union.
Disjoint union, exactly. Coproduct of topological spaces.
The same should work.
Yes, this disjoint, but in this case, if there are topological spaces, we need to describe the topology, so also disconnected union. Just coproduct of groups. This is a bit confusing. Yeah, so when we talk about product of groups, we want something such that map to it will be the same as map to the first group and then map to the second group. And now we want something such that maps from it will be the same like maps from the first group and the map from the second group. Do you know such construction?
The free group, right?
It's a free product. It's a free group if we. Yes, so exercise. Coproduct of groups. To describe it. Coproduct of pointed spaces, pointed sets. Some candidates?
Disjoint union.
So if they're not pointed, then of course you're right, disjoint union. But if they are pointed, the wedge sum, the bucket, yes, because if they're pointed, if you just take the disjoint union, you don't know how to point it, so you just glue the pointed. Yes, so if you have two pointed sets, so this is the way the coproduct will look like. And by the way, if there are two intervals, it looks like this. Let's talk about topological space, also the same. And by the way, if there are two, the product will look like this. And you see that there is canonical embedding, canonical map of the coproduct into the product, in this case. But you don't see it in case of sets. If you don't have pointed things, and if you just have this joint union, then you don't know how to map it to a product, because you have to choose something. And here it looks very natural and canonical. So when something looks so natural and canonical, you suspect that it comes from the categorical world, that it can be done in general. And then you see that it cannot be done in general because in some categories it cannot be done. And so you start to suspect that something is wrong here, and you're right. It can be done in general, but under some additional conditions. It is categorical construction, but it's not obvious. And it doesn't always work. Okay, now fiber product. Definition, fiber product. So fiber product is a product in the over category. In over category. So we can spell it out. We have X, we have Y, we have Z, we have such diagram. So X times Y over Z is such object, such that first of all, this diagram has to be commutative. And secondly, for any other, so W, such that this diagram is commutative, there exists a unique, sorry, again doing the wrong direction, exists a unique error like this, such that this entire diagram is commutative. So let's do sets. What is fiber product in sets? Somebody? So in fact, I never know how to pronounce it correctly. Should I say fiber product or fibered product? Let me check it now on the web. here it's written fiber product. But in sets, what it actually means, it's product of each fiber separately. So do you know what is a fiber? Somebody? I'm sure that at least 3 of
The
you know
image of a
what is a
point.
fiber. What?
The image of a point.
Per-image of point, exactly. So you run over all points of Z, and you take the product of the fibers over this point, of the per-image of this point. And then you take union of everything. So it's in each, over each point of Z, a product. So this is something that works very well with something that's called as a relative point of view of Grothendieck, saying that it's saying two things, that if you have some theory of some objects, so it's very good to think about family of objects. Family of objects which should be parameterized by something continuous, and the first thing that you can parameterize is objects from the same theory. So family of objects in C parameterized by an object y in C is the same, is more or less definition or point of view, I don't know how to call it, it's even not really a definition. It's a morphism from X to Y. And how you think about it as family. So in order it to make some sense, you need some notion of a point. The category should be somehow geometric, say topological spaces or sets or varieties of manifolds. And then if you have point, and you have map from a point to y, this you can think as an actual point in y, you can consider the fiber product, which you will call the fiber, because in case of sets, fiber product with an embedding of a point is actually the fiber. And each time you have a map between x and y, it means that you have lots of fibers, so you can, for any point, to get a new object. And when you make a fiber product of x and x prime over y, it's basically the same as to make it relatively over each point to take a product. And in general, each construction that you can do for your original category, you can also do for the over category. It doesn't have to exist, but often it does. And when you do it for the over category, you basically did it for the relative case or for the case of family. So you did it simultaneously for all the objects in the family, or at least this is a way to think about it. So this is a relative point of view of Grothendieck to think about the over category and constructions in general, families in general. Yes, so you can also define fiber product of topological spaces. So since in sets, or you always, in fact, do you always have? Not always, but okay, exercise. If P in C is terminal object, then x times y over p is x times y. So fiber product over a terminal object is just the product. And okay, so what does it give? So it gives a map. So
Is it true that in the over category, I think it's obvious, but I want to make sure that in over category, the terminal object is the over one, the one we are over?
So okay, another exercise, I think I told it. So if no, I didn't tell it. You're right. If C is terminal, B and C is terminal, then over P is I cannot say it like this. Sorry. Okay, I will say
that
it.
if no, I
So the over category of P is canonically equivalent to the original category C, but I didn't say what is equivalence of categories. But in this case, you can easily realize what does it mean. So any object have a unique morphism to the terminal one. So when I say here equality, of course, it do not really mean equality. I mean canonical isomorphism. So the exercise to find isomorphism, and the fact that it is canonical is just convince yourself that it's the only reasonable choice.
I asked Morgan the opposite question, I think, that
So,
the other direction, that
what do you
if in the category over P, for example,
I see.
then P is terminal.
Yes. Oh yeah, it's good exercises. Exercise x in of maybe I would write it more explicitly. X to x with identity in over x is terminal. Yeah, it's a good example. When you take the over category of some object, you know what is a terminal object. Just this one. Okay. And yes, so Fourier product over the terminal object is a terminal object. This gives you a map from x times say sy to x times y. So maybe I will say in general. So another exercise given, again, not well defined exercise, morphism from S to S prime concept. Yeah, am I right? Yes, I think I'm right. So given such a morphism, you can always construct such a morphism. Yeah, but in fact, even more generally, yes, you don't need a terminal object. Another exercise is construct x times y over s to x times y. This you can do even if there is no terminal object, basically by the definition of product. So when you say construct something, you use the definitions of the categorical constructions here. You know that you have some unique morphisms, so you use them in order to get this construction. So in case of sets, you can see that this is actually a subset of this. This map is actually an embedding. For sets, you see that it's one-to-one. So for topological spaces, you just repeat the same construction, you get a subset of the product, and then you take the topology to be the induced topology. Here you see that the Fourier product, what is the Fourier product? Is a pair of 2 points, point in x, point in y, such that they are mapped to the same point in S. So this is a subset, and in fact a closed subset, usually. Yeah, I think even always. No, not always. If S is housed off, it's closed. If not, not necessarily. So this is a subspace, which is the fiber product with the induced topology.
Can you please explain again the exercise you gave one before that, and maybe also this?
This one?
Yes.
So here it's not I gave, Tal gave it. So if you have the over category of X, so you have this object in the over category of X, so the map between X and X with identity. So this is an object in the over category. The exercise is to prove that this is a terminal object. So now to explain this exercise.
Yes.
So this is not mathematically well defined exercise because I ask you to construct something. But okay, I do mean just to construct it. So of course, there is some freedom. Yeah, I cannot say what is a correct construction and what is a wrong one, but once you know it once you see it. And let me change here the order. Maybe we'll start with this because this is simpler. But in general, since we're working now in category theory, we have here lots of categorical constructions. So each time I write some categorical construction, I mean that I assume that it exists. So the product doesn't have to exist in general. But if it exists is unique, you're unique up to unique isomorphism. So I know what I'm talking about when I say product. And when I ask you to construct, I mean that I ask you to use the categorical properties, both of this and of this, in order to describe the morphism between the first one, between this and this. In case of sets, you see immediately what it is, because fiber product in case of sets is the collection of all pairs, x and y, x is element in x, y in y, such that both of them maps to the same element in S. And product is the same collection, but without any condition, just pairs, x and x, y and y. This is it. So one is subset of the other, so you have a natural map. But now try to repeat it for a general category, but here you can't talk about elements, but you can say, okay, you have such diagram, you have such diagram, by this property you have to have a unique morphism like that will satisfy something, so let's take this morphism. And this here the same, little bit more complicated.
Is there any criteria when does the subcategory preserve the product or such?
Yeah, there is such a notion, yes, but okay, usually it's called a little bit differently, but yes, okay. But criteria, yeah, probably there are some criteria, but I'm not sure there are too many of them. Usually, you will start with this as a criteria for something else. Okay. Another exercise that I forgot to say, I should have said it before. Co-product of okay, we say abelian groups, I said, and of many abelian. So co-product of abelian group is not the free product, because the free product is not a group, not a abelian group. It's just the product. So here you see kind of miracle that happens, that co-product and products are the same. But then if you go to infinitely many abelian groups, then suddenly you get exactly again that they are not the same. Then the co-product of abelian groups, of infinitely many abelian groups, will be actually the, like in vector space, it will be direct sum. Like that always everywhere you get 0, and the product will be actually product. Okay, I have 3 more minutes, and the next topic is limits. So 3 minutes is not enough for limits. So maybe better you will ask some questions.
We define infinite product.
Yes, I said it before, I didn't write it down. So for any collection of objects, you can talk about products of them, just the same definition, but with with all your objects downstairs. And the same with coproduct. So if it's finitely many objects, then you can see it's the same, like as to do it iteratively, as to take first times the second times the third. When I say the same, I mean that there is an isomorphism. Formally, I mean that there is an isomorphism, and informally, I also mean it is canonical, meaning that it's unique, that it satisfies some reasonable conditions. It's not unique, but if you put some reasonable conditions, it's unique.
Chami, I have a question about the criteria for it to be toward the definition of canonical isomorphism for the universal property that you said, the unique isomorphism. I think, but I want to make sure.
Can you repeat about what? I didn't. Okay, maybe you ask a
About
question.
About what is the criteria that you need to say in order it to be canonical, in order the isomorphism will be unique. for the product.
For the product, okay.
For the product.
So in the case of product, I said it is just that the diagram will be commutative.
No, but when two what isomorphism between two implementation is canonical or not?
So
When it is canonical. I
this
think-
is okay. This it's part of the definition of a product. Yes. So okay. And when you no, so it's canonical always because canonical depends on the context, and once you say that it is a product, you mean that you have this context in mind.
Yes, but I think
But
that
if you want it to
there
be
is a
unique,
criteria.
so unique. So I said that the product is x times y is an object x times y together with two projections. So if you have another product, so another candidate for the product, let's call it z, but it's also coming equipped with two projections, then this morphism have to be unique. And if they are both products, so we also have morphism to the other direction. They're both isomorphisms because the compositions have to be identity. So there is a unique isomorphism such that this diagram is commutative. So this is basically the additional condition that you have to impose on the morphism between two candidates of a product, in order, or two implementations of the product in order to be unique.
So basically, it is unique in this special category.
Yes, in the over
Okay.
category, in this category CXY, in the
Okay.
over category of XY. But it means that it has to be a morphism, yes, in CXY and not just morphism in C. Here we pay for this abuse of notation because we say product, we think sometimes about an object in CXY, and then it is unique up to unique isomorphism. But sometimes we think about morphism in objects in C together with something that make it morphism in a CXY. But when we think about the object itself, then we think about it as object in C, and then of course the isomorphism is not unique. So yes, so we pay for this abuse of notation, but it's probably worth it because otherwise it will be very cumbersome. Yeah, I looked at Google on fiber product, and I find a Wikipedia article on pullback of in category theory, which is basically fiber product, then fiber product of scheme. But then the third thing was images and some products with fibers that you can eat. Okay, maybe now I'm late, but now I still want to say this thing. We talk about fiber product. There is a dual notion in the opposite category. So fiber product in the opposite category are called push-outs. So definition, push out is fiber product in and again you can spell it out directly, and maybe this is a little bit more interesting to see what you actually get. So if you have two sets x and y and a set z and two maps like this, so you can define the push out. And here you see something funny. If the maps between z to x and z to y are embeddings, then the push out is something very nice and natural. It's x union y modulo some equivalence relation that you glue z. But if the maps are not embeddings, then you see that this equivalent relation is not a relation. And once it's not a relation, not an equivalence relation. And so you have to take a transitive closure to get equivalence relation, and then it's something which is really unpredictable. So push out you can do with sets, you can do with topological spaces, but the answer often will not be Hausdorff. So in many examples, push outs are more problematic. And you can do push out of groups. So I think it's called amalgamation product. GH. It's denoted as free product, but over something over K. If K is usually it should be a subgroup, but you can do it for any map. K is in G in H. And so it's a good exercise to compute push outs also examples of categories that you know.
And the quotient topology is when x equal y. The idea of quotient topology.
You can present it as a push out, yes. So
but when x equal to y, and you use the function is z to x.
Quotient topology is not x equal y, so if you want to get quotient topology, you want to take this, I think. Push out of this is x modulo z.
Why this is embedding? It
not
does
embedding.
not have it.
But I didn't say that push up exists only for embeddings.
But you did.
I
You
said
did
that for
the
embeddings
injection.
it's nice. Oh, here. Yeah, sorry. This is not injection, and this is of course also not injection.
So z in x
This is
does not have to.
Z to x formally doesn't have to, but if you want to talk about quotient topology, you want to take a quotient by some subset. I'm
Okay,
talking
but
now
I'm
about
asking-
subset, not equivalence relation. A quotient by equivalence relation is a special case of something that is called equalizer or co-equalizer, which you can also write via push out. But okay, but this is better to discuss in the general setting of a limit, and I will talk about equalizers next time. Okay, for now we are more than twice slower than I planned, but probably it's okay. Any questions? Okay, so next week there are no holidays, everything as usual, yes? So see you in a week.
Thank you. Goodbye.
Bye-bye.
Goodbye.
Thank you.
Thank you.
Thank you.
Bye. Thank you.